Now we have already understood what it means by Young's modulus, that is the stress-strain relationship in the case of a metal bar, and we are only talking about the linear stress and the linear strain. Now we want to understand how the Young's modulus changes with length, area, and temperature. So here is a simple experiment. There is a bar of length L, and of course there is a cross section area of A associated with this bar, and when I apply a stress of force F, okay, then the length of this bar changes from L to delta L. We want to understand, if I increase the length or decrease the length, how does this stress by strain relationship changes. So Young's modulus in this case would be equal to stress, which is force divided by area. The whole thing would be divided by strain. Strain in our case would be delta L by L. Now we will understand, if I change this area, what happens. If I change the length L, what happens. So, and of course the temperature, we are changing the temperature of the bar itself. So if I change the L, then how does the stress by strain changes? See, the stress would not really change, so that of course would remain the same, because stress is equal to force by area, and neither the force nor the area, cross section area of the bar is changing. We are only changing the length of the bar. So instead of using this length L, now we have started using length L dash. What about strain? The strain also would not change with length, because the delta L dash would also proportionally increase with L dash. Okay, so as I increase the length, this delta L, the change in length with the same amount of stress, would also increase proportionally. It would increase in the same ratio. In other words, this is equal to delta L by L, and therefore the strain also remains constant, and therefore the Young's modulus does not really change with length, which is to be expected, because just like specific gravity, the weight, specific gravity, mass, charge, all of those things, Young's modulus is the intrinsic property of the material. So Young's modulus of steel would be the Young's modulus of steel, no matter what kind of length of the steel bar is, or what the cross section area is. Now let us look at the cross section area. See, as far as the cross section area is concerned, we are applying a force. How does that force translate into stress? That force, what it does is that it stretches the molecules of the material, and the bonds between these molecules, they are like springs. So those springs, they get increased in size. Okay, they change in length. Okay, and when I remove this force, then those springs return back to the original position. So the bonds of these molecules, between the molecules, act like springs, and these are actually the bonds. Okay, so that is the picture that should come to your mind. Now what happens if I change the cross section area? Then the number of these springs actually increases proportionally. So the same amount of stress, the same amount of force is spread across the larger area, and therefore the strain in any of these one such spring actually decreases. Okay, so if my area changes from A to A dash, there is a proportional decrease or increase. There is a proportional change in my delta L. So my delta L also becomes delta L dash. Okay, in such a way that A by A dash, the change in area, is actually equal to the change in proportionally same as the change in length. Okay, not the change in length, but the variation in length. Okay, so those two are proportional. So now that is the stress with the cross section area. So what happens because of this? Now let us just write it. Young's modulus, we can write, we already know the formula for the Young's modulus. What is the formula for Young's modulus? That is equal to is equal to stress by strain. Stress is F by A and strain is delta L by L. In the new case, what would happen is that in the new case, our new Young's modulus would be F by A dash divided by delta L dash upon delta L. Now these two would be equal because, delta L dash by L. These two would be equal. Why? Because our A by A dash is same as delta L by delta L dash. Okay. So with the cross section area as well, the Young's modulus that does not change. Okay. And that is to be expected again, like I said before, Young's modulus is the intrinsic property of the material. It does not change. It is just like specific gravity. It does not change. It is intrinsic to the material. And the way to understand it is that if I increase the area, then the same force is applied across several different molecules, and therefore the strain of each of the molecules actually decreases, which means that our delta L actually decreases as I increase A dash, and that decrease or that change is proportional. Okay, so by the same proportion as I change the area, my change in length would change by the same proportion, keeping the Young's modulus the same. The last thing is the Young's modulus with temperature. Now with temperature, what would happen as I increase the temperature of the material? These bonds, these molecules would be held less tightly. Okay, so at low temperature the molecules are held more tightly. So this spring would be tighter at low temperature and little loose at high temperature, which means if I apply the same amount of stress, the change in the length would be larger at higher temperatures. So my strain would increase with temperature for same amount of stress. Because my strain increases with temperature, my Young's modulus would actually decrease with temperature, and that is the relationship that is seen here. The Young's modulus for aluminium with temperature, and for that matter for all kinds of materials, the Young's modulus actually decreases with the increase in temperature. So the temperature is increasing, the Young's modulus is actually decreasing, and that happens because for the same amount of stress, my strain actually increases. The length by which these springs would elongate actually increases as temperature increases, because the molecules, they become more energetic. Hopefully things are very clear. Okay, Young's modulus does not change with length and cross section area. That is the most important thing you should get out from this class. Questions are asked on that all the time. Okay, if you look at doristatutor.com, you will again find many questions based on this concept. Thank you.